going to get the session started. Dr. Gillian Eggleston with the LSU AgCenter Audubon Sugar is going to talk about insoluble starch.
Good morning. It's always great to speak at ASSCT, the Louisiana division. And I'm going to talk today about insoluble starch. We now know it contributes to lower sugar exhaustion for molasses. And I was very pleased to hear Elizabeth yesterday from Domino Refinery, and she mentioned that they're looking now at insoluble and soluble starch in the raw sugars, and she stated how both of them affect the refinery process. And I'm going to show you today we now have evidence to show the insoluble starch is affecting the factory processing. So my presentation outline, I first want to make sure we all know what I'm talking about when I say starch and how does it change at the factory. And then the measurement of total soluble and insoluble starch. Then the study we did, we compared the exhaustion of final molasses across 2 grinding seasons, 2020 and 2021, from 3 Louisiana factories. So I have a lot of data. And then I'm going to discuss control of insoluble and soluble starch at the factory with hydrolyzing amylase enzymes. And then we'll look at solutions to prevent or remove carryover or residual amylase that sometimes happens in the raw sugar and even in the white sugar, and then major conclusions. So what is starch? How does it change in the factory? Basically, starch is glucose in a long chain, what you call a polysaccharide. And you can see 2 polysaccharides here. They're both made up of glucose, but one, amylose, is linear, and the other is branched. And they're both absolutely packed densely into a granule, and that is the insoluble starch. And if we look at the granule in cane juice, the starch varies with botanical source, but in sugarcane, they're very circular, they're very small, 1 to 5 microns. So when we extract juice from the cane, it's mostly in the insoluble form. Now, before 2013, it was in 2013 where we had an extremely high starch year. And at that point, we thought the insoluble granules that are extracted into the juice, in the presence of heat, water, and with time in the factory, that insoluble starch swells, and we get swollen granules. And then with more time and heat and water, it disintegrates, and we end up with our soluble starch. And that's important because amylase always breaks down. It's always easier to break down soluble starch than the dense insoluble starch. But we now know that's true. We've done a lot of work since 2013, and this is more the scenario that's actually happening in the factory. Again, it comes in as this small granule, 1 to 5 microns. Some of it swells, some of it doesn't. So we have different sizes. Some of it stays in the insoluble form, but some disintegrates. So we end up in the cane product. This could be masquite, molasses, raw sugar, where we have a mixture of soluble starch, disintegrating starch, and swollen starch. And when Elizabeth mentioned about gelatinization, she really meant the swollen starch that affects the filters in the carbonatation refinery. So because of this new information, we had to come up with new methods, because all the conventional starch methods in the industry only measured total starch, and a lot of that was underestimated because it wasn't totally solubilizing all the starch. So we came up with a research method where we could measure insoluble, soluble, and total starch, which you use a sonicator. And then because the sonicator is quite expensive, about $3,500 US, we came up with a factory method, and that was recently, last year, accepted as an international ICOMSA method for raw sugars. But in that case, you just need a microwave oven that you can go out to Walmart or anywhere and just buy one. And how does it work? Basically, we now know the factory product contains insoluble and soluble starch, so we need to make sure it's completely solubilized. We do that with microwaving and sonication, and then you take absorption of Y minus X will give you the insoluble starch. The advantage of this method is it's about 6 minutes. It applies to all factory products, but as I said, the disadvantage is the sonicated cost. And I just want to mention, we get a lot of raw sugars now at Audubon every month from around the world, where we're being asked to look at insoluble and starch in raw sugars. I'm going backwards. Okay, so now we go to our molasses exhaustion study. Audubon does a weekly molasses survey across the whole entire grinding season, and we use the conventional bricks. We do sucrose, glucose, and fructose with HPLC. We also use polarimetry, and we measure conductivity ash. We measure target purity, and we also measure true purity with the HPLC. And it's the difference between the true purity and the target purity gives us the true target purity difference. And that is an indicator of how well you're exhausting your molasses. The lower the TPD, the better you're doing. And I just want to mention, we know that the reducing sugar ash ratio has a big effect on molasses exhaustion because it affects solubility of sucrose. So results. So here we have 3 factories, and I've got them as E, H, and I going down. We have the first column is 2020, and the second column is 2021, and this is across the whole season. And in the column, the blue column, we have the TPD values. In the green, we have fructan polysaccharide. In the orange, we have dextran, and in the yellow is the total starch. And I also put the mean values for TPD, and the first thing you can see that it was worse. The TPDs were worse in 2021 than 2020. And in these studies, we didn't find a clear relationship between TPD and dextran or fructan, but in other years we have. So we can't rule those out as affecting molasses exhaustion. But I want to point out the differences in the factory E, both years had high TPD, but factory I at the bottom, both years had the lowest TPD values across the season. So we looked at the conventional way. We look at it, reducing sugar ash ratios and the TPD values, and as expected in 2020, there were some correlations which you would expect, particularly for factory E. It was worse for factory H, but there was a moderate weak correlation for factory I. But in 2021, the correlations were basically extremely low, so there was something else going on that was affecting the exhaustion that year, as well as the reducing sugar ash ratios. So we looked at the starch. I mentioned earlier the fructan and the dextran didn't seem responsible. And here we have the 3 factories, E, H, and I, 2020, 2021, and we have the average seasonal starch. So that's an average of about 13 points. And you can see in 2021, factory E and H had much higher starch, total starch. Factory I didn't have very similar numbers, but you can see even though it had higher starch in 2020, we still had a lower TPD, and you have to look at the insoluble starch. The insoluble starch was much lower in that factory, and we can see that even better here if we look at the percentage of soluble starch, the percentage of insoluble starch. So in that year, in 2020, yes, it had higher total starch, but the insoluble starch was much lower than the soluble starch. And that's probably why it had a better TPD. And I want to point out, look at factory E, 26% was insoluble, 74% soluble. So we're finding quite a bit of insoluble starch in the molasses. And it has to be something that's gone in the factory that causes these different ratios, because what comes in extraction is mostly insoluble, as I said earlier. So we know with factory I, something went on in that factory that caused the less insoluble starch than soluble. It did a better job at solubilizing the starch in that factory. So then we plotted the average insoluble starch and the soluble starch with the TPDs, and the first time we've ever found correlations, high correlations with starch. And we can see as the insoluble starch went up, the TPD went up, and vice versa, because then you'll get more soluble starch if the insoluble starch has been solubilized. So the extent of solubilizing your starch in the factory is affecting your molasses exhaustion. I also want to point out these 2 points. So each point represents one factory per season, and that factory was the one that had the low TPD each year. And we went back to this factory and we said, what were you adding? They were all adding amylase. And when we asked them, they were adding high temperature stable amylase. For some reason, it was doing a better job at controlling the insoluble starch. And we think what's going on is it's that swollen insoluble starch that causes the greatest viscosity. So it's most likely the viscosity is being affected by the insoluble starch and reducing molasses exhaustion. Here's an interesting slide where we put total starch on the bottom x-axis and percent soluble or insoluble starch on the y-axis. And we found that there's a cutoff. When you have greater than 3,800 ppm of starch in your final molasses, then at that point the factory, they were unable to solubilize all the starch. So you started to see an increase in the insoluble starch. And that's because the more starch that comes into the factory, the more you have to solubilize. You've got more starch to solubilize, and it's going to be harder. And this really confirms what we saw in 2018, when we had an extremely low TPD values that year, to the point we were picking up TPDs of 1 and 2, which were unheard of. And in that year, we found the low starch contributed to the molasses exhaustion. But in this year, too, we also found fructan and the dextran as well. So I don't want to rule them out, but I do think we've confirmed now the starch is definitely affecting molasses exhaustion. And previously, people would say they didn't, and that's because they were using the wrong methods. The methods weren't detecting all that insoluble starch. So how do we control this at the factory with the amylases we have? Well, it's complicated. We have different types of amylase. We typically use the intermediate stable temperature amylase, which is effective up to 85 degrees centigrade. But the high temperature stable amylase is stable to higher temperatures. And the trouble with that, and I've mentioned this before, is that because they've been developed for washing machines and dishwashers, the high temperature stable amylase, and small amounts of amylase activity can sometimes be found in raw sugar, and then you send it to the refinery, and it goes through the refinery, and it ends up in refined sugar and molasses. They sell it to their end users, such as a starch pudding manufacturer, and it messes up the texture. Luckily, this doesn't happen very often. But there have been times when refineries have added HT-stable amylase as well, which is an absolute no-no. And also, it's much harder to control starch at the refinery because you're dealing with 65 Brix liquors. That means there's less water, and these enzymes are hydrolyzing enzymes. They need water to work well. So it's always better to control the starch at the factory than the refinery. And the difference, because of the HT amylase, is more stable at higher temperatures. You can add it to the clarified juice, whereas typically we add the intermediate stable enzyme to the next to the last or the last body of the evaporators because we know there's more soluble starch there. So we looked at both high temperature stable and intermediate temperature stable amylases at 1 and 5 ppm doses to clarified juice, simulating what goes on in the factory. And you can see here that the high temperature stable amylase does a much better job at reducing the starch. But it was interesting to find that both of the enzymes worked best in the first 10 minutes because a lot of the enzyme would become denatured in that hot temperature. In the red line, you see an increase, and that's because some of the insoluble starch in the clarifier is being solubilized, and that's why you see an increase. But the action of this work of these amylases was all dependent on their heat-stable activity. But the downside, as I said before, is that with the intermediate temperature-stable amylase, we found no carryover activity in the raw sugar, whereas we did find it with the high-temperature-stable amylase, even at 1 ppm. And this is a visual of what I'm saying. So with no amylase in a clarified juice under the microscope, it's full of small particles, including starch. When you add the IT amylase, you can still see a lot of swollen starch, even insoluble starch. Whereas when you add the HT amylase, it was much cleaner. We didn't see anywhere near the insoluble starch granules or swollen starch. Excuse me. Okay, now I've just explained what's going on, but we need solutions. There are solutions to this that we're looking at and we know about. So we can either prevent or remove carryover amylase during processing, either at the factory or the refinery. And that would allow us to use this high temperature stable amylase, which is going to do a much better job and help with molasses exhaustion. So there's a new enzyme from Novozymes in Brazil that was developed. It's called Primera, that they're adding. And then we know that activated carbon, when used in the refinery for decolorization, also removes the carryover amylase. This is from the Primera website. They're basically saying you add the Primera to the clarified juice or the mixed juice, and the temperature range is 80 to 100 degrees C, which is kind of intermediate between the IT stable enzyme and the high temperature stable enzyme. And the whole deal is they're showing that you can really reduce your starch even at small ppms, but it causes no carryover amylase. But they have not used the method that we have to measure total insoluble and soluble. So we really want to do trials here in Louisiana. We tried to do them at the end of 2023, but we are working with a factory to get this enzyme, and we will be doing trials in Louisiana this year. And they have been reporting for a few years now, if you use this enzyme, you improve your molasses exhaustion by 1.2 to 1.5% without carryover amylase, which kind of ties in with what we found. And that's a lot of money. That's a lot of money to save for a factory. The other way to do it is the activated carbon. You use this in the refinery. If we used it in a factory, it would get saturated very quickly. We have a lot more impurities to deal with at a factory than a refinery. So it's always going to be better to use it at the refinery. And we know that the more surface area that the activated carbon has, the better it's going to be at removing the carryover amylase. And at the at the refinery, you can either add granular activated columns, but there are some refineries now who are using powdered activated carbon with special filters. So major conclusions: all factory products, starch exists in both soluble and insoluble forms. A 2-year study of final molasses from 3 Louisiana factories showed that the amount of solubilization of the starch in the factory affects molasses exhaustion. Insoluble starch directly reduces exhaustion of sucrose from molasses. High temperature stable amylase controls insoluble starch much better than the IT stable amylase at the factory, but there is the risk of carryover residual amylase. But the good news is we have possible solutions, either adding Primera at the factory, but we want to see if this works in Louisiana. And we want to validate and verify it ourselves, or activated carbon at the refinery. So I want to thank you, and I want to acknowledge the American Sugarcane League for sponsoring this research. Thank you.